Video we're going to talk about inverse functions. When f from your domain A into your codomain B is 1 to 1 on a set, so when we restrict the function, C contained in A, we'll draw script C, there is a natural function from the image of C under F back to C, which assigns a unique point in C to each B in the image of C. This is the inverse function. And we'll denote it F inverse from the image of C, that's our domain, into C. So let's get some quick examples out there. Well, how about f of x is equal to 1 over x? Well, the inverse here is simply f inverse of y is equal to 1 over y. And it's defined on y such that y does not equal 0. How about f of x is equal to e to the x? Well, it's invertible on the set 0, infinity, and on that set the inverse is f inverse of y is equal to log of y. Actually, we should probably not close that. That doesn't actually obtain 0 except at infinity. So here it's defined, and so this would be our script C, and this would be our inverse function. Now in economics, we want the inverse demand function. Right, and so we'll know what the inverse demand function is once we figure out what the demand function, right? Well, the demand function takes the price P and computes D of P, the quantity that will sell at price P. So P is equal to D inverse of Q is the inverse demand function, IDF. And what does it compute? It computes, you give the value Q, which is the quantity that will sell, and it gives you the price at which that quantity you can sell that much for. So when maximizing profit, or when computing profit maximizing output, This is very useful. And why is it useful? Well, let's give a simple example that we can solve using just one-dimensional optimization, which we should know from calculus. So the example, suppose your profit function, right? So P is equal to P times Q, the price that you sell times the quantity that you sell. So this is equal to D inverse of Q, and suppose this is all a function of Q, and you want to know what Q is, right? Then this holds true. Suppose that demand decays logarithmically with the price, so that Q is equal to the demand at P is going to equal to, say, the negative log of P. Right? So as the price increases, the consumer is exponentially uninterested in buying this much stuff at that price. Well, then if we invert this function, then P is equal to D inverse of Q is equal to e to the negative Q, just by inverting this. And so when you plug this all back in, you've got P of Q, P as a function of just Q, is now equal to this D here times Q, which will be Q times e to the negative Q. And we want to maximize this. This is a 1D calculus problem. So what do? We calculate a derivative. Right? So we've got to use product rule and chain rule, and it's not so bad. So dP over dQ of Q is equal to, well, product rule will give me e to the negative Q minus Q e to the negative Q. And now I set that equal to 0. So I find the extrema by solving this equation equal to 0. E to the negative Q minus Q e to the negative Q is equal to 0. Well, I can cancel out e to the negative Q from both sides because it's always non-zero. And so I've got that 1 minus Q is equal to 0, or Q is equal to 1. That's not the end of the story, because Q has to be greater than or equal to 0. So it could be that my maximum is actually Q is equal to 0. You doubt it, right? But it could have been, and we have to check, right? Well, the profit at 0, of course, is just 0. And the profit at 1 is equal to, you work this out, it's just e to the negative 1. And so we conclude that maximum profit, if we produce Q is equal to 1 unit of the good.